Hi, and we're very happy to have Mathew Bullimore from Durham for the last talk of the conference, talking about unitary categorical symmetry.
Okay, thank you very much, and thanks for the chance to speak. I'll try to send you all away with happy thoughts about unitarity. Okay, so here's the team. So we've all been trying to think about things to do with unitarity and how they interact with generalized or higher categorical symmetries. So it's with my postdoc Andrea in Durham and my students Thomas and Jamie. I should also thank this pair as well, but I mean, I think their net contribution to writing the papers has been negative, so I can't really give them a good recommendation. All right, so what's the motivation? Well, in the last few years, I've been trying to think about the mathematical structure of categorical symmetries, the type of structures that they have that go beyond groups and involve categories and higher categories. But not just what the structure of the symmetries themselves, but how do they kind of act on and organize the spectrum of observables in quantum field theory. And that's involved a lot of high representation theory, not just in what the symmetries are themselves, where it describes things like higher dimensional versions of Wilson lines, but also in how the symmetries act on observables in the sense of local operators or states might transform in representations of a symmetry, but if we look at extended defects, you might expect higher representations to appear. But today, well, in most of this business, and what I've been doing at least, kind of principles like relativity or relativistic symmetry and unitarity we haven't paid too much attention to. And so those are the type of questions that I'd like to ask, is how do relativity and unitarity interact with these problems? How do they change or dictate the structure or the mathematical structure of the symmetries that we're dealing with? All right, so I want to begin with kind of a broad outline or scheme, and in some sense this is more like a wish list because I think, as far as I'm aware, the underlying mathematics is not yet quite on firm footing. But nevertheless, I want to give a kind of outline of the type of structures we expect and then give some examples. Okay. So we'd like to encode in a nice, clean way ideas about relativity and unitarity in relativistic field theory. So I'll be in the Euclidean setting here, so that will really mean unitarity will really mean reflection positivity. And there's a nice clean way to capture these type of structures that I learned about from Fried and Hopkins' paper, which involves choosing, well, it's basically it's a way of encoding the type of fields you have in your theory and what type of space-time symmetries you have. So the standard type of thing is if you just have bosons, it might be an oriented theory, and the relevant structure group is SO. If there are fermions in the game, then you might want the structure group to be spin. And then if you start including time reversal as well, then there's some more intricate structures. So in some sense, relativity or the type of fields you have in your theory can be captured by this structure group that I call H or H sub D. And then what Fried and Hopkins showed in the context of topological field theories is that in order to understand unitarity, then you can introduce a slightly enlarged or extended symmetry group that adds in a reflection and is able to capture, or is important in order to capture unitarity as well. So I'd like to think about, when we think about symmetries, categorical symmetries, or perhaps gapped systems with symmetries, I'd like to think about fixing one of these first, and then asking, having fixed this type of internal symmetry structure, what type of mathematical structures are we dealing with to describe symmetries? So what should it mean to have symmetries in a unitary theory, or how are we going to capture symmetries in a unitary theory? Well, I should say, yeah, first of all, if this looks scary, I'm really only going to focus my examples on the oriented case, which is the standard thing we see involving fusion categories or spherical fusion categories or unitary fusion categories. But in principle, all the others are there and can be studied too. Okay, so here's the obligatory picture from this conference. And so one way to try to encode unitarity is basically to ask for the symmetry TFT to be unitary in some reasonable sense, and then ask what that implies. For example, if I look at the gapped boundary where the symmetry structure lives, what structure do I then get from that? So as I said, I want to kind of be in a world where I fix the symmetry type first, or an internal symmetry type, and then I want to formulate symmetries in terms of a symmetry TFT in one dimension higher. And, well, in my talk, I'm going to be looking at very kind of finite symmetries. And the symmetry TFT in particular, we're going to require that it's a fully extended TQFT. It should be H-structured, so for example, it might be oriented. And it should be unitary in some sense. And then there'll be some other conditions as well, some additional conditions, which is something like requiring the symmetry TFT to be like a condensation defect in some higher dimensional, trivial higher dimensional theory. Having seen Dan's talk this morning, I get the feeling that might be related to things he had to say. Okay. But I'll give an example of what this means later. So then the basic idea is like, okay, you have this structure for the sim TFT. It should be unitary in some sense. Well, then given that, what structure do I get on the gapped boundary where the symmetry itself is supported? The symmetry algebra is supported. And whatever that structure is, I'm going to call it, well, I'm going to give it a fancy name and call it a H-hat dagger D algebra. So there's a bunch of things there. The H-hat is this structure group we talked about at the beginning, or the extended structure group. The dagger is reflecting the fact that this has something to do with unitarity, perhaps. And the D algebra is reflecting the categorical degree here. And so it's something like a higher fusion category, a multi-fusion category with a bunch of extra structure involving some daggers and interplaying with this group H. The honest, well, in truth, I don't really know exactly how to describe this structure in general, but I think that's a bit of a dream. But at least some recent work, in particular, this work at the bottom here, gives us some hope that we can really define these things. But they're not too fancy. Here's some examples. So in one dimension, and I asked for an O-dagger algebra. That's symmetries of a one-dimensional oriented theory. They should be something like a C-star algebra, like in quantum mechanics. And there's a bit of extra structure there coming from the sim TFT. Or perhaps if we're in two dimensions in a unitary-oriented theory, then there's the typical statement that the symmetries should be captured by a unitary fusion category. Okay. So these things are not too outlandish, at least in cases that are commonly studied. And so, but you might ask, well, from a physical point of view, perhaps, what is the role of this structure? There's a lot of stuff going on here. There's a lot of dagger structure going on. What is its role? What is its purpose? And perhaps, how does it relate to more standard notions of unitarity in physics, like in ordinary quantum mechanics, for example? You might think about at least invertible symmetries acting by unitary operators on a Hilbert space. How do these structures relate to that type of ordinary unitarity? And so what's the idea? Well, one thing you could ask, or one purpose you could give to this structure, is that, well, you imagine taking your field theory and you put it in some type of situation where you actually expect a Hilbert space. So, for example, you might study the theory on a sphere times time, where you actually get a Hilbert space, and then you might ask, well, if I take my symmetry defects and have them act on the Hilbert space, that they should act, well, if they're invertible, they should act by unitary operators. More generally, you might ask them to form something like a C-star in quantum mechanics. And that will capture some notion of unitarity. So this is one thing that you might ask, is that if you take your symmetry category in higher dimensions and you, in some sense, compactify it on some spatial manifold such that you get a Hilbert space, then those things should act like symmetries should act in quantum mechanics, basically. And then you recover some ordinary notion of unitarity. Okay. And so this thing, this notion of compactification here is closely related to factorization homology. There's other names that are used in specific cases, like tube algebras and things like that. Okay. So this is the kind of general broad scheme. We want to, think about the symmetry TFT as being unitary, ask what structures does that give you on the gapped boundary, and then perhaps ask, well, how does that actually relate to ordinary unitarity in quantum mechanics? Okay. So having given this kind of very broad overview or wish list, with the real risk of telling you something very trivial, I'm going to focus mostly on one dimension and a little bit about two dimensions. And then if you're interested in what exactly we know higher up, or at least what I know higher up, then you can come and ask me afterwards. Yeah.
So it's often the case that with categorical symmetries, they act on Hilbert space mapping the untwisted Hilbert space to the twisted Hilbert space.
Yep.
When you talk about Hilbert space in this context, what do you have in mind?
I mean precisely as you say, the full twisted Hilbert space. So including all of the twisted sectors of all various kinds you can imagine.
Okay, thanks.
And that's what this structure here is capturing. Thank you. And that is indeed very important in this business. If you try to truncate to just the untwisted sector, you're not going to capture unitarity. So I think there's another question that we'll answer. Exercise to do.
I'm trying to frame that in things I understand, in the framework of things I understand. So the old-fashioned thing would be we have a d-dimensional field theory, and we understand what unitarity means there. Okay, so now what you say is that we have a d plus one dimensional field theory, perhaps with boundaries, perhaps with boundary conditions, etc. If I just look at it as a d plus one dimensional field theory, couldn't I just copy my previous understanding?
I think you could, and apply that to the symmetry TFT. And what I'm saying is that
the symmetry TQFT, if I understand correctly, is a topological field theory in the bulk.
yes, that's right.
But that has already been worked out, I think.
Yeah.
Okay.
Yeah, that's right. So I'm saying all I'm really saying is, let me require that symmetry TFT is unitary in some sense, and then ask what structure am I getting on the gapped boundary. And that should capture what I mean by unitary categorical symmetry.
Is it obvious that for unitary symmetry, you need to have the sim TFT be a unitary TQFT? I mean, you make this as an input assumption, but is that actually necessary?
I don't know. I'm going to take it as a definition, and then we'll explore to what extent that is good.
I think it's clear that the answer is yes.
Yeah.
But just think of the whole setup as a d plus one dimensional field theory. This whole setup has to be. Think of the whole setup as a d plus one dimensional field theory. And then it is just a particular case of a d plus one dimensional field theory. The whole thing has to be unitary. Another way of saying it, you can just squash the sandwich and you get something which looks like a d-dimensional field theory.
But you could imagine a unitary, boundary condition, but the bulk is not necessarily unitary.
Well, that would, unitarity has a tendency of, lack of unitarity has a tendency of leaking out to other things.
So what's the question? Whether that was like a...
I think it's clear that the whole thing has to be unitary.
Okay. So let me talk about one dimension at the risk of saying trivial things. So let me just start with quantum mechanics. So symmetries in quantum mechanics operate as commuting with the Hamiltonian. So you can move them up and down a line freely. And if I restrict attention to finite symmetries, then they should form a finite dimensional C star. But the star is coming from the adjoint of an operator, and the C star structure is encoding some notion of positivity that they should act on Hilbert space. And if we're dealing with finite symmetries, finite dimensional symmetries, this is a finite dimensional C star algebra, and these are all direct sums of matrix algebras. So, okay, an example is a group algebra, for example, for a finite group, where the dimensions of these numbers n's would be the dimensions of the irreducible representations. And so I could ask then, well, what does the sandwich construction look like? So in a sandwich construction, I'd like to have a two-dimensional TQFT. And I'm going to be in the oriented world here, and it should be unitary in some sense. And these things are classified by, well, Frobenius algebras, and in the unitary world, there should be C star Frobenius algebras. And there's a bit of extra structure there in specifying that. So in particular, underlying it is certainly a C star algebra, a finite dimensional C star algebra, say a sum of matrix algebras. And that's the algebra of boundary topological operators that live on regular boundary condition. But there's a bit more structure, which is that of a trace, which gives the Frobenius structure. And so in physics, that's coming from the disk partition function with an operator inserted. So there's a bit more structure there coming from the SymTFT, perhaps. But it also involves, having done so, it also involves a bunch of extra choices. So there are, in this very finite case, there's just a set of positive real parameters, lambda, involved in specifying this trace. And you can think about those as Euler terms or Euler counter terms in TQFT. So this seems like there's a lot of extra structure. But, well, okay, what is this structure doing from the SymTFT point of view with regard to unitarity? Well, one way to view it is that what this extra trace gives you is actually a Hilbert space structure on the algebra itself. That's one way to view it. Sometimes called a H star algebra. And, well, what's going on physically? Well, that's just the Hilbert space structure you get from the 2D field theory by studying it on an interval with the gapped boundaries on each side. A picture like this. It's also just the finite version of the GNS construction. So you might ask yourself, well, shouldn't we fix these? We've got these extra parameters compared to just a symmetry. Shouldn't we perhaps fix those, the Euler counter terms? And I think the answer is yes. And one way to require or to fix them is to ask for this two-dimensional bulk, this SymTFT, to be a condensation. So this is the kind of extra condition that I alluded to earlier. One way to think about it, well, is that that you're freely allowed to kind of expand and collapse holes, so you can, using your gapped boundary without cost. That might be what we mean by condensation, because we can then insert a bunch of holes and expand them until we get a network. And what this does is it basically fixes all of these Euler counter terms to be proportional to the rank of the matrix algebras. And this gives you what you might call a special Frobenius algebra, or what I might call an O-dagger algebra. Okay, so why did we do this structure? Well, one reason to expect that this is a good thing is it seems to be true in examples of SymTFTs that we like. So for example, digraph-Witten theories have exactly this property, and those are the things that describe invertible symmetries. So here's that example. An example is if you just have a finite group G. The symmetry algebra is the group algebra. And that arises on a Dirichlet boundary condition in digraph-Witten theory, 2D digraph-Witten theory, and it has exactly this property, or this condensation type property. So that's what I want to call an O-dagger algebra. There's a bit more structure there than just a C-star algebra, but the crucial thing is having a C-star algebra, which is capturing unitarity in this sense. Okay, so then let me say a few words about two dimensions. Let's now move up a dimension. So we're now interested in symmetries in a two-dimensional field theory, which means the bulk is three-dimensional. And so the structure on the boundary is some symmetry category C, and we normally require that this is a unitary fusion category or multi-fusion category. So in my language, I want to call that an O-dagger 2 algebra. And in this instance, the bulk, the SymTFT, is the associated derived zero theory built from that. And in this case, you can ask, now, how do the symmetries act on the theory? One thing you can do is you can put the theory on a circle now and have the defects wrap the circle. And one way to think about that is you're reducing, in some sense, to an effective quantum mechanics. Alternatively, if you're in a CFT, you can think about local operators. And that's often the framework where you see this structure, where you recover what's called the tube algebra. Representations of the tube algebra are things that control how these non-invertible symmetries act on local operators, or more generally twisted sector local operators. And one basic result, or one known result, is that if you start with a unitary fusion category, in the normal sense, then this tube algebra that you get by wrapping defects on a circle again has the structure of a C-star algebra, and a bit more structure as well. And so in this sense, you recover some standard notion of quantum mechanical unitarity in the old-fashioned sense. Okay. So here's an example of that, just to give an example. So you take a Tambara-Yamagami symmetry, specified by the abelian group A, and then there's just one non-invertible line, which has some fusion rules like this. And then there's some additional data fixing the associators involving the non-invertible line. And you can compute the tube algebra, and in particular, so the relations in the tube algebra, the algebraic structure involving the non-invertible line looks something like this. So it acts in a non-invertible fashion. It's definitely not a unitary operator, but it still forms part of a C-star representation. So you're still capturing a good notion of unitarity in quantum mechanics. So in this case, you can enumerate these irreducible representations. There's a finite number of them, and you can check that's how things transform in unitary CFTs, for example. Okay, so I think I'm coming roughly towards the end.
5 minutes.
5 minutes. Okay, good. So let me just finish with a conclusion. So I've tried to give kind of a few very basic examples. And so one thing we've been trying to do is just to expand the landscape of examples that we can study in this way. So moving up to higher dimensions where higher fusion categories are relevant, and also studying other choices of tangential structure, spin O or pin plus minus. And one of the main type of ingredients that you need to do this business or play the same kind of games that we've been playing in the symmetries world is some good replacement, for n vector spaces. And this is to say that even studying the trivial symmetry is already quite hard in this setting. this structure of vector spaces or n vector spaces just underpins everything else that you're doing, forms the basis. And so having a good replacement for that in this setting is really important. So that's one thing we've been trying to understand and to build. And then applications, well, you can, once you have the structure of these symmetries, you should expect that how you describe things like 't Hooft anomalies, perhaps gap systems with those symmetries will depend on the structure. So there should be applications to those things as well.
Okay, any question for Matt?
So in your last case of the Ising, when you say the representation, do you mean a unitary module category or the Ising? When you say a representation of the Ising theory, do you mean a unitary module category over the Ising category?
No, I mean the 1+1 critical Ising model. And what I meant by this is that there are 9 irreducible representations. And so in this CFT, I think each of them is realized once by the chiral primaries. So it's kind of minimally has all of the things in it.
So I'm a bit confused about the one-dimensional case.
Okay.
So if we consider the 1+1D TQFT with Ising symmetry, which is given by the regular module of Ising category, then I thought we have 3 local operators, topological local operators, so 3 idempotents, and the traces are proportional to the quantum dimension of the lines. So there's a line with the √2 quantum dimension. So how do I match that with the requirement that the traces must be integers?
I think we might be looking at a different setting to what I have in mind here. You're thinking 2+1 here.
No, 1+1.
1+1.
1+1, Ising symmetric 1+1 TQFT, which has 3 local operators, idempotents, and the traces on each is proportional to the quantum dimension of the 3 lines in Ising category. Mm-hmm. So one of the local operators have quantum trace given by √2, proportional to √2, let's say. Mm-hmm. But in the one-dimensional example, you had traces given by some integers, right?
Yeah, but I'm not viewing that theory as a SymTFT, right? So earlier on, what I was doing, your example is 1 dimension up from what I was considering earlier, right? What I was saying earlier about a 2-dimensional field theory, I was viewing that as the SymTFT, the topological field theory, where I'm imposing kind of extra constraints.
Okay, maybe we can discuss. Yeah, thanks.
Yeah, of course. Stacy, any more questions?
Any more questions? Oh, so Sakura has an announcement to make.
Okay, Matt first. Thanks, Matt, again. So also thanks to all the speakers, all the posters, all the Gong Show participants, all the participants for the questions and the interactions. Let's thank everybody. Dinner, we opened up the floor for a 2025 Symmetries conference, and no one really came forward except my co-organizers for the next year's KITP program, which will take place in the spring. And there's a conference there, and most likely the 2025 will take place there. So together with Mason, who just left, and Shuhang, and Michaela, and myself will organize it in Santa Barbara. So hopefully you'll come to that as well. So thanks everyone, and see you in the spring on the beach.